So today I'm going to review the William Lowell Putnam math competition. Apparently it's one of the hardest math competitions in the world. So we're reviewing the very last problem of the 2022 paper, B6, saying that we should find all functions from the real positives to the real positives, such that f of x times f of y plus f of y times f of x is equal to 1 plus f of x plus y. So by allowing x to be equal to y, just substitute y in x, you get 2f of f of x times f of x is equal to 1 plus f of 2x. Because we replace y with x here, making 2x here, y with x here, making x f of x, and y of x here, making x f of x. Add these two to get 2f of x f of x. So we also decide to let y be equal to 1 in this situation, where we substitute y1 is equal to here and y1 is equal to here, right? And because we have this for f of 1, we assume it let be some function k and rewrite the said equation. As a result of this, we then decided to, let's say, divide by f of 1 here, as we divide every term here by f of 1 in these functions. So that returns into, instead of just x f of 1, I just call it n for notation's sake. So f of n plus f of n over f of 1 is equal to 1 plus n f of 1, n over f of 1 plus 1, which is just n plus f of 1 over f of 1. As a result of this, we match this accordingly to find f of n specifically, and then substitute into the original equation back here. This equation is already equation here anyways, so we just basically match these equations up and match certain values such as 1 and f composite 2x over f of 1. So therefore we get this is also equal to this, that f of x plus 1 over f of 1 is also equal to f of x over f of 1 plus 1. If you assume bijection, we can allow that f of 1 is equal to 1. Meaning that we get like three situations. We already know that the case one being that f of x is equal to a even power, the degree of f of x is equal to 0 mod 2, that it could be true for f equals 1, but not necessarily to satisfy the bijection for all positives. We could allow the degree of f of x is equal to minus 1, and f of x is equal to x. But the thing is that if you substitute f of x is equal to x in this equation, you don't get, these sides are not congruent to each other, so only case 2, where the degree of f of x is equal to minus 1 is valid. So, I allow let f of x be equal to 1 over x plus b. The thing is that we're trying to find the constant of b where there is some positive a where it satisfies. So we substitute into here and get these results. And leading that 2ax plus 2b over x is equal to 2ax plus b plus 1 over 2ax plus b. We expand to get likewise here. And therefore, we have this equation. Because we're mainly trying to sort out for b, we're trying to find the discriminant of the function here, where it's equal than or equal to 0. Because the fact that this 4a squared minus 2a is equal to 2a minus 1, 2a times 2a minus 1, and we factorize the 2 from here, we get 16ab squared multiplied by 2a minus 1, and we get here anyways. After the expansion of the equation, we get minus 16a squared plus aa plus 1, or multiplied by b squared, plus, in brackets, 3 minus 8a multiplied by b plus 1 is greater than or equal to 0. As we're solving for b, we say that b is at least this. Is at least this function here. So in order to find the minimum value of b in the set of positives, we have to try and find the limit of such equations. Meaning the limit of a approaching some constant, not necessarily 0, but near 0, such that aa minus 3 plus minus the square root of 128a squared minus 8ta minus 5 all over minus 32a squared plus 16a plus 2. We try to do it at a equals 1, where b is less than or equal to 1, 6, plus root 43 over 30. But because of the fact that that's 1, we could do even lower than that. And I'm not even sure if that would even be correct. So we decided to use L'Hopital's rule on that limit to get this equation here by find the derivative of this function and this function respectively to get this and this. So when our a is equal to 1, we get around 8 multiplied by 13 times root 43 plus 10 in brackets, all over 49 root 43, because we allowed a to be equal to 1 and substitute into these equations. As a result, we exponentiate downwards because this is 104 and this is 49. So we cancel out the 43 to get 1 over 4 over 49 plus 10 over 49 root 43. And that is less than, or that's at least around, less at least equal to 2 times 6, 2, 6 of 49 over 49 plus 10 over 49 root 43. But the thing is that that's at 1. The thing is that this function is decreasing as it tends towards 0. So this is going to go below this as a approaches 0 from 1, b eventually approaches 1, allowing b to near basically equal 1. So therefore we get the equation that f of x is therefore equal to 1 over ax plus 1 for some constant a within the positives. Thank you for listening to my video on arguably the hardest problem of the Putnam Math Competition 2022. Bye.